so I'm like basing my grade off anybody else.
I love the little quote. When I die, I'd like my group project people to
To lower me down so they can let me down
one last time.
I've heard variations of that, but that works well, I guess.
I love that so much.
Yeah. Yeah. So, yeah, I've heard that in response too, so like, you know, you give to substitute the Cincinnati Reds or something like that. So, okay, so reminder of where we were these many days ago. So we were doing Newtonian cosmology. We had a sphere of uniform density, and so within the sphere, which at some time t has radius r sub s, m sub s is the amount of mass within it. The sphere is uniformly expanding. Magically, it's been made, it's all flying apart uniformly. And uniformly meaning that the density within the sphere is uniform at all times. But as the radius of the sphere expands, certainly the density is decreasing. The density becomes smaller over time, and so that's represented here. The mass inside the sphere stays constant as it expands, and so that's going to be 4/3 pi times whatever the density is at time t, times the radius at time t cubed. And because of the fact that this thing is described by this uniform expansion, we say, okay, we're going to define the scale factor, which tells us how many times bigger is the sphere at some given time than compared to how big it was when the scale factor is set equal to 1. So we can pick some standard moment, if you will, when the scale factor is equal to 1, and we'll call r sub s the radius of the sphere at that time, whatever time we pick to be the standard time. And we call r sub s the co-moving coordinate because that doesn't change as the sphere expands. It always refers to the radius of the sphere at the standard time when the scale factor was 1. And so this captures the idea that it's the same mass within the sphere as it expands. That isn't changing even though the radius of the sphere is expanding. Okay? Any questions? What questions do you have? And then we derived the energy equation, which said that 1/2 times the speed of the surface squared is gm over the radius plus u, and we interpreted that in terms of representing conservation of energy. Soon we're going to say, okay, now just waving chicken feet, here's the general relativity result, which is a slight change from, which is a change from the Newtonian result. One term looks quite plausible, the other term is just like, okay, well, I'll just have to take your word for it. Okay, so if Rs, if the radius of the sphere is the scale factor times r sub s, little r sub s, the co-moving coordinate, which doesn't change with time, the co-moving coordinate is a constant, then we can take a derivative with respect to time. And we'll use the convention that dot over a symbol means ddt of that symbol. So Rs dot is equal to a dot times Rs. There's no plus a times Rs dot because the co-moving coordinate is constant. It labels the surface of the sphere. So the energy equation becomes Rs squared a dot squared. It's just another way to write capital Rs dot squared is Rs squared a dot squared is equal to 4/3 pi times, actually I'll put that before pi over 3 times g times Rs squared times rho of t times a of t squared plus u. So here we've used the fact that m sub s is 4/3 pi rho rs squared. When we divide by rs, I'm sorry, rs cubed, when we divide by rs, that just leaves rs squared. And so then we put in that rs squared is a squared little rs squared. Okay, everybody on board? All right, let's multiply by 2 over little rs squared a squared. And that's going to give us a form which gets a little modified when we go to the GR version. So if we do that, we get a dot over a, quantity squared, is equal to 8 pi big G over 3 rho of t plus 2u over rs squared times 1 over a of t squared. And this is what we call the Friedmann equation in Newtonian form. It's not the Friedmann equation because that's a GR cosmology equation, but we are going to wave some chicken feet and change this into the GR version in a couple of minutes. Unless I can't get this chalk to come out, then we just have to quit.
Chalk out so you know.
Yes, that's right. Feed the chalk. All right, the Friedmann, what? That kind of Fried. The Friedmann,
The regular.
it's a German. All the big things are from Germans.
Everybody.
The Friedmann equation.
Physics.
Physics. In Newtonian form. All the big names are German, he said, and then wrote Newtonian. Okay, maybe not all the big names are German. So let's note here that a dot and a only appear as squares. And that means that you could change their sign. You could change, if you change them to, sorry, you don't want to change a to be negative. But in other words, if I change the sign of a dot, if I made it negative, that's perfectly fine. So really, yeah, it's not, I guess it really all that matters. A dot only appears as square. Only appears square, let me put it that way. Because we don't want a negative scale factor, what does that mean? So a dot only appears squared, so contraction a dot being less than 0 is just the time reversal of expansion. A dot greater than 0. So it could go either way. The sphere could be expanding with time, it could be contracting with time, and if you kind of made a movie and played it backwards, the movie played backwards would be the solution if a dot is less than 0. The movie played forwards would be the movie if a dot were greater than 0. But we're going to focus on expansion since the actual universe is expanding. up here for now because I'm gonna want to refer back to it, so I'll wall it off on myself there. What questions do you have? Shall we continue our quest to understand the universe? All right. So suppose u is greater than 0 over here. If u is greater than 0, then both terms on the right-hand side are positive. Because certainly the density is positive, g is positive, 8 pi and 3, those are all positive. A squared is certainly positive, and rs squared is certainly positive, so everything is positive on the right-hand side. So that would say that a dot over a squared is positive. If u is greater than 0, RHS, the right-hand side, is always positive. So a dot is going to be greater than 0 at all times. And that says, expansion forever. There's not enough gravitational attraction to ever stop the sphere from expanding. Every part of the sphere, in a sense, is moving faster than escape speed. And so it just keeps flying apart forever and ever and ever. Question, Alec?
Yeah, doesn't it not matter what u is since it's a dot over a squared?
But u could be negative. And so we're going to treat that case too. If u is negative, then here's a positive term, here's a negative term, and they change with time. And so what happens is eventually they become equal to one another, and a dot over a at some time becomes equal to 0.
Okay.
So what happens is it expands up to some certain limit, and then it starts falling together.
Okay.
It's like you've thrown the ball up at less than escape speed, and so it eventually reaches a maximum height and comes back down again. Our dust universe, so to speak, expands to a certain limit, stops, and then starts falling back in.
Would a dot over a equals 0, would that be when it's back to a point? Or?
No, that's when it has reached its maximum size. Because that says a dot is equal to 0, so it says that the radius is no longer increasing. So it's like if I throw something up, if I throw this chalk up in the air, right, then its height, y, increases to some maximum height, and then when it's at its maximum height, y is at its largest value, but y dot, the derivative of y is equal to 0 at that moment. The speed is equal to 0 at that moment. And then y dot becomes negative. So it starts falling back down again. And our universe kind of does that. In other words, the surface of the sphere reaches some maximum size, and then it will start to shrink in radius after that. And note, by the way, that we've got this sphere and we've got a surface of it here, but I could also just as well take any sphere within it and follow it, and every sphere within it does exactly the same thing. It's a uniform expansion, so if I consider the material on a surface that's half the radius of the whole sphere, that surface is half the radius of the whole sphere at all times. It's a homologous expansion, and then it would be followed by a homologous contraction. If you look at the equation of motion for the surface of any given radius, then what you find is that, for example, if it has half the radius of the whole sphere, its acceleration is always half the acceleration of the outer surface of the sphere. And therefore, its velocity is always half the velocity, and therefore its radius stays half the radius of the sphere as a whole. So let's look at what happens if u is less than 0. If u is less than 0, then A dot starts out positive, since we assume initial expansion. We could start out negative if we assume initial contraction, but we're assuming it's expanding. And again, in our Newtonian universe, you would have to have done something special. It's not hard to get a homologous contraction. In other words, if I start with a uniform density sphere and then I just release from rest, it will automatically collapse homologously. To get it to expand homologously would require some prestidigitation. You would have to somehow manage to get things moving initially so that how fast things were flying away from the center was proportional to how far they were from the center. Well, that would take a lot of work to actually make that happen. So we're just saying, whatever, God did it, or whatever, to make this uniform expansion. Then A dot starts out positive, since we assume initial expansion. But there's a maximum value of A when A dot is equal to 0. So what we're going to do is, it's actually a little bit clearer. Instead of working with our Friedmann equation, we'll work with it written in this form, the form where we did not plug in that m was 4/3 pi over r sub s squared, r sub s cubed. We'll go back to equation 1. So that would say that in equation 1 here, when is the velocity of the surface going to be equal to 0? Well, it'll be when the right-hand side is equal to 0. It'll be when u is equal to minus gm over r. So this will be from 1 u would be minus g m sub s over r sub s. Or in other words, g m sub s over a times little r sub s, because remember, big R sub s is the scale factor times the co-moving coordinate. Little r sub s is equal to minus u. So I'll just move the minus sign over to the u. And a reminder, what we did is we set the right-hand side equal to 0 in equation 1 to get that. So A max, the value of A when this happens, when A dot is 0, which will be equal to A max, will be equal to minus big G times m sub s over u times little r sub s. That would be the value of A max. It's got a minus sign. Looks at first like we're saying that A max is negative. No, because u is negative here, right? We assume u is less than 0. A max is greater than 0 since u is less than 0. A dot becomes negative after A max is reached. And our Newtonian universe, if you will, here, starts collapsing. So there's an analogy for that in general relativistic cosmology, where you could have a universe conceivably that expands out to some maximum scale factor after a Big Bang, and then starts falling back on itself and approaches a, some wag named Gnab Gibb. Where did that come from? Not Gnag. Totally ruining it. Gnab Gibb. Gnab Gibb.
Big Bang spelled backwards.
Big Bang spelled backwards, yes. The opposite of Big Bang is Gnab Gibb. So a recollapse into a singular is Gnab Gibb. Also call it Big Crunch, but I like Gnab Gibb better. I think that's funnier. Okay. If u is equal to 0, then notice what happens there. If I set u is equal to 0, then as r sub s keeps increasing, drs dt gets closer and closer to 0. So drs dt approaches 0 as the scale factor approaches infinity. So that's analogous to throwing a ball up at exactly escape speed, so that after infinite amount of time it's no longer moving anymore. Whereas if u is greater than 0, that's you're launching at greater than escape speed, so you fly away, and after an infinite amount of time, you're still going. There's a finite limit that the speed approaches. If u is launched with less than escape speed, then you reach a maximum height, fall back together. Interpreting in terms of our Newtonian cosmology, it's all about the kinetic energy of the universe compared to its potential energy. If it has enough kinetic energy in this expansion, more kinetic energy than gravitational potential energy, it flies apart forever. But if there's more gravitational potential energy than kinetic energy, you can come back. And if u is equal to 0, then we would have a situation where it expands forever, and in the limit of infinite time, it comes to a halt. It approaches 0 speed of expansion as t goes to infinity. A dot approaches 0 as t approaches infinity.
So as you enter the black hole.
What's that?
As you enter the black hole.
As you enter the black hole. And well, this won't really. Oh well, no, not quite. Because this is becoming infinitely large in size as opposed to like an event horizon or anything like that.
I meant like, since all the time flashes before your eyes, you would quote unquote see.
Oh, I see. So you'll oh, okay.
Yeah.
I see. If you want to experience this, just fly near the event horizon of the black hole, come out the other side, and look around. Okay. Sure. Good plan.
Where's it?
Good stuff.
So,
Yes.
you
You know it. Okay. Wait. I really need to.
You make one of those longer.
the figures are long as they're almost.
Those aren't true.
Okay, great. Anyway.
Physics, yeah.
Yes. The correct Friedmann equation using general relativity is A dot over A squared is equal to A pi g over 3c squared epsilon of t as opposed to 8 pi g over 3 rho of t. It's 8 pi g over 3c squared epsilon of t minus kappa. This is supposed to be a Greek kappa. Kappa c squared over r naught squared 1 over a of t squared. Very important equations, one of the fundamental equations of cosmology. And thus will be our equation 2. So we have to say what the new symbols mean. One of those new symbols is epsilon. Epsilon is the energy density, the energy per unit volume. But this is relativity, so we include in that rest energy. So we'll note that this is plausible, since for non-relativistic particles, epsilon will just be the mass density times c squared. Epsilon is rho c squared for non-relativistic particles because they have almost no kinetic energy. Their energy is almost entirely their mass energy, mc squared. So if there's mass rho per unit volume, that times c squared would be the rest energy per unit volume. Non-relativistic particles, the kinetic energy is only a slight correction to that. But this is valid even if the particles are relativistic, such that most of the energy is due to their motion as opposed to due to their rest energy. Note this equation is still valid, even if this equation is still valid even if the particles are relativistic. So the plausibility part again is that before we had 8 pi g over 3 times rho, and rho is essentially epsilon over c squared for non-relativistic particles. But in general relativity, all forms of energy gravitate. It all counts. Rest energy, kinetic energy, it all contributes to gravity. So we have to incorporate that into our equation. Kappa is what's called the curvature constant. So here is where things get all general relativistic. In other words, this is all related to the shape of the universe. Kappa tells us the shape of the universe. Because the universe can be a curved space-time, it can have different shapes. Now, to simplify, we typically, even though it's certainly not true, but on the largest scales, we assume that the universe can be considered to be homogeneous and isotropic. In other words, the same from place to place and the same in every direction. So for that to be the case, the density would have to be constant everywhere. Well, that's not the case. If we look at the large-scale structure of the universe, we see superclusters of galaxies separated by voids that are like 100 or so million light years across. The universe has a large-scale structure which is kind of like this, like soap suds in a way, where the matter is concentrated in superclusters of galaxies that are like the soap in the soap suds, or the sponge in the sponge, so to speak, the substance of the sponge in the sponge, or the breadiness of the bread, and these voids are the bubbles. And so the universe is not homogeneous and isotropic, but on the other hand, if you average over regions that are bigger than a few hundred million light years, then it does seem to be, on the whole, it looks the same from place to place, as long as you make the volume you're looking over big enough. Well, what we're going to assume is, for simplicity, is just assume a universe that is homogeneous and isotropic, with uniform density everywhere, and figure everything else is just details. And, of course, you know, sweeping it under the rug again, so to speak. But it does simplify things. And it's possible to show that for a homogeneous and isotropic universe, it has one of three and only three possible shapes that it could have, according to general relativity. Yes, what questions do you have?
Would taking into account within the voids if there was dark matter, would that bring it closer to isotropic?
It doesn't, because the dark matter is actually the clusters of galaxies formed in concentrations of dark matter. So the voids also would have less dark matter in them as well.
Okay.
And, you know, again, this is the kind of thing where it almost sounds like, you know, cosmologists spend a lot of time doing this. Because what we think, but there's good reason to think this, is that this large-scale structure of the universe arose when quantum fluctuations in space-time before inflation, which we haven't talked about yet, but we will, quantum fluctuations that existed before inflation were stretched to macroscopic sizes after inflation, after a sudden rapid increase in the size of in the value of the scale factor. These slight density fluctuations in the very early universe then became places where dark matter could start falling in and concentrating first, and then later ordinary matter, baryonic matter, followed it. And so these were the seeds of large-scale structure. And so the large-scale structure of the universe today is thought to have started with microscopic quantum fluctuations before inflation. But it all makes sense, is what it comes down to. So, I mean, it's really amazing what it comes down to, but it just sounds like, seriously, but it's the best explanation we have. It really is.
That's all
Where?
discussed.
I just want to make sure.
Yeah.
The world isn't flat. It's actually an oval.
Except what we'll find is that the universe should be flat, as a matter of fact. Kind of disappointing.
They were right all along.
Kind of disappointing. The universe is flat.
Oh, just so you know, Nicole and I made a group chat for the astronomy traveling course,
Oh yeah,
and we titled it the Flat Earth Society.
the Flat Earth Society. You died.
Well, we got two less going on the trip.
What?
Yeah.
Actually, less people going.
Right.
I'm gonna bring
the spots there and play.
I'm gonna bring the level onto the plane.
You do that.
It makes sense.
You know, I saw this thing recently, said something like, only 78% of millennials are sure the Earth is round or something like that. It's like, oh my God, millennials are so stupid. It turns out, though, you ask any question where you think everyone would know that, and like about a third of the people don't know that, or something like that. Like, you know, the number of people who don't realize that the Earth doesn't go around the sun once every day, I mean, it just makes makes you want to throw up. It's unbelievable, you know.
Science literacy.
It's like, were you paying attention at all when you were in 3rd grade?
I know.
No, is the answer, or whatever. Anyway, isotropic, same in all directions universe. For a homogeneous isotropic universe, the universe can have one of 3 possible shapes. It could be flat. The most boring possibility, but the one which we think is right. Flat means kappa is equal to 0. So in the Newtonian version, it corresponds to the u equals 0 universe, the one where it's going to, if we didn't have dark energy, expand forever and halt in the limit of infinite time. That would be the classic result, but it turns out that dark energy changes that. More on that later. So flat, if kappa is equal to 0, the metric is that of special relativity. ds squared is equal to c squared dt squared minus a of t squared times the quantity dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So notice that piece right there is just the usual spherical coordinates expression for the spatial metric. So we're just using spherical coordinates in our universe. But the twist is the a of t here. In other words, it's expanding with time. So this looks just like you would get if you had, well, if we made it two-dimensional. I could have a rubber sheet and I draw polar coordinates on it. And then if I just uniformly stretch the rubber sheet, then it stays flat the whole time. It gets bigger and bigger, but the only correction we need to make is that the r is a co-moving coordinate here, and that the actual distance from the origin is the scale factor times r. So this, in 3 dimensions, would be you have just what you always think of as 3-dimensional space, and it's just uniformly expanding. And so we have to keep track of the fact that the distance from the origin isn't given by little r, it's given by the scale factor times little r, because little r is the co-moving coordinate, which says how far you were from the origin at some time when we decided that the scale factor was 1. So, does that make sense or not? Do I need to further expand upon that? My default might be yes, unless you're just going to say, no, I get what you're saying there.
Maybe say it again.
Okay, so let's consider a plane, okay? Like this black world here. I can put polar coordinates on it. Right, so some point, and so its distance from the origin is A of t times r. In other words, normally in polar coordinates we just say r is distance from the origin, but we have an expanding rubber sheet. So we say the distance from the origin is A of t times r, because the sheet is expanding, and so we need to account for that. So when the scale factor is equal to 1, this co-moving coordinate is the actual distance from the origin. But at any other time, it's more or less than that. So there's a little ant just standing in place right there, and as the sheet expands, the ant's getting further and further from the origin, but as long as the ant's not crawling around, then its value of little r stays fixed, because little r is how far it was from the origin when the scale factor is equal to 1. That doesn't change with time. How far it was from the origin when the scale factor is equal to 1 is just whatever it was then. As the sheet expands, little r stays fixed, and A takes care of the fact that its actual distance from the origin is getting bigger with time. Does that make sense? And then meanwhile, here's the angle phi that it is away from some direction, like it could be our x-axis. So the fact that our rubber sheet with our ant on it is expanding is accounted for by having that scale factor right there that says how far it is from the origin versus how far it was when A of t was excuse me, equal to 1. And so the metric on the rubber sheet, just for spatial distances, for ordinary polar coordinates, the metric is dr squared plus r squared dphi squared. That's ordinary polar coordinates metric, written, distances in polar coordinates because, well, just because it is, okay. How do we account for the sheet being expanding? Well, it would be that you just have to multiply by A of t squared. A of t squared times dr squared plus r squared dphi squared. Because, remember how we get the ordinary form in the first place is if I make a little displacement, I can resolve it into a component dr in the radial direction and a component r d phi in the phi direction, in the azimuthal direction. And so ds, that displacement there, is going to be ds squared is dr squared plus r squared dphi squared, which is from the Pythagorean theorem. But if the actual distance from the origin is A of t times r, then these both get multiplied by A as well. This would be ADR. This would be AR times dphi, because AR is how far you are from the origin. And ADR is how far you moved away from the origin. And so therefore ds squared would be A squared dr squared plus A squared r squared dphi squared. So you can factor out an A squared and use that as the correction to the spatial metric that represents the fact that this is an expanding sheet that's changing size with time. Does that clarify the issue?
Yeah. Question. What would the two-dimensional case of this represent? Would it be the spatial separation?
We're only talking about the spatial part of the metric. Right, the time part of the metric is the usual c squared dt squared.
But why wouldn't it have the third component of r squared times theta?
Oh, I'm just doing the case where we were, where our space was two-dimensional.
Yeah, okay.
If we had two-dimensional space-time, then we would just have, this term would go away because there's no theta, no polar axis now. And this term would be, sine squared theta would just be 1 because we would be in the equatorial plane, and so theta would be pi over 2.
Okay.
And so we just get the r squared dphi squared term.
Okay.
Right. So in 3 dimensions,
It's that.
it's just, this is the piece now. This is the piece, right? This represents what happened in 3 dimensions. Okay? Any other questions? So, in our usual way, we'll set dt equals d theta equals d phi equals 0, so that only r is changing. That says that A of t dr is the proper distance along a radial line from the origin. So the total proper distance, notice this A of t dr corresponds to this right over there. A of t dr is a little radial displacement. So that the total proper distance to a point with radial coordinate r is what we were already saying that it was. It's going to come up here, so I'll erase it from over there right now. We'll call that d sub p of t, the proper distance as a function of time of our ant that is just standing in place on the expanding rubber sheet, or expanding or our raisin in the expanding raisin cake of our universe here. dp of t is equal to a of t integral from 0 to r of dr equals a of t times r. Again, that's exactly what we were just asserting before. You were just saying, well, the metric says it's that. I was just asserting that over here, that this is going to be the way it works, and the metric says that's right. You actually get that directly from the metric without starting with the assumption that this is how it works, but this is how it works. So, one more thing before break. Thus,